Well, good evening, everybody. Welcome to another Our Universe Revealed. My name's Jonathan Crass, and I'm the coordinator of this public lecture series from the Department of Physics at the University of Notre Dame. Thank you for those of you who filled in that form about where you're coming from. It gives us an idea, and it's great to see that we have people from all over the US joining us this evening. As well as coordinating the program here at Notre Dame, I just want to welcome all of our regular attendees back who joined us last week. And if you joined us for the first time last week, welcome back as well. I'll consider you one of our regulars now, given the circumstances. If it's your first time with us this evening, thank you for joining us. It's a pleasure to have you here with us. If you want to know more about our upcoming events over the next few weeks, please go to our website, nduniverse.org. You can see it there on the bottom of your screen. We can sign up to our mailing list there. And you can also find out more about our events on our Facebook group. The format this evening is going to be very similar to last week. We've got about a 30-minute talk followed by some questions. We'll be collecting those questions throughout the presentation. If you're using Zoom to watch this, you can do that via the Q&A button at the bottom of your screen there. If you're on YouTube, there's the chat on the right-hand side that you're able to fill in and send us questions all the way through. You also have an option to send us questions via a Google form. We've just put that link straight out now into the Zoom chat as well as into the YouTube chat. So if you want to prefer that way of sending any questions in, we'll collate those and then come back and answer those at the end. There's also going to be some questions all the way through the talk tonight to give you a chance to engage a little bit, just like we did with that poll at the start. We'll take those questions and wrap them up as we go, and we'll see what you think about some of this stuff rather than just having me speak to you all the way through this evening. Because not only am I your host tonight, I am also your presenter, as well as running the public lecture series at Notre Dame. My full-time job is actually designing and building instruments for telescopes. I've been doing that at the University of Notre Dame now for a little over 5 years, working on an instrument called iLocator, which I'm going to tell you a little bit about this evening. That instrument's designed to search for planets similar to Earth around other stars in the night sky. Before that, I worked on another instrument called the Adaptive Optics Lucky Imager, which is shortened to AOLI, as we call it. And I did that while studying at the University of Cambridge for my PhD. So I've now been working on designing and building these instruments for almost a decade. And so I thought I'd give you a little bit of a peek behind the curtain of how we do that, some of the processes we go through, and how we kind of design and build these instruments that study the cosmos all around us here on the planet Earth. So without more ado, let's get started with the talk. So I'm sure many of you will either have a telescope yourself or will have had an opportunity to look through a telescope previously. So telescopes really collect the light that we see coming from the objects in the night sky. And astronomers sort of give them the nickname a lot of the time as light buckets. Effectively, they're just like a bucket that you put outside, and if it was raining outside, the raindrops coming down would collect in that bucket. For telescopes, instead of collecting rainwater, raindrops coming down, we're simply collecting light. So hence the name light buckets. Now, that bucket of rainwater isn't particularly helpful. It just collects that rainwater. And just like the same with telescopes, telescopes themselves collect that light, but they don't do much useful with it. So that's where an astronomical instrument comes in. It's something that goes behind that telescope to record or measure that light. Now, the first task for you this evening is I'm going to put you on the spot for those of you watching live and ask you what kind of thing you might think of as an astronomical instrument. So if you have a cell phone or another device that's connected to the internet, you just go to that web address on the screen there, polev.com, and enter NDUniverse. You should see a question there, and you can type away with some words and things that might describe the sort of thing an astronomical instrument might be. The camera might be an idea somewhere, so you can have a look at there, see what you think, and we'll pop those answers up on the screen in a couple of minutes once you've had a chance to respond to that. I can see some responses coming in there now, so that's great. So don't worry if you're still working the way through that. We'll give you a couple more minutes. Excellent. There's some great answers coming in here. So while they're still coming, I will pop up the ones that we've had so far. So you can see there's a lot of people saying cameras. We've had things like prisms, binoculars, something like that, a spectrometer, spectrograph, cameras. So these are all great answers. We'll see if we have a few more coming in. And while they're going through there, and I'm sort of, those answers are all coming in, which is fantastic. I'm going to give you a few of the answers that I thought about, particularly from a historical perspective, that astronomers might have used before. So back in the old days, astronomers didn't have cameras. All they had was their own eyes to study the night sky. And so what they did is they used to sit in cold telescope domes, simply staring at the night sky and then drawing sketches of what they saw. This is actually a drawing of Warren de la Rue that was actually made in 1852 using a 13-inch telescope, where he was studying the Saturn, and you can see its rings there that many of you are maybe familiar with. You can also actually see, if you look carefully, down here at the bottom of the screen and also on the right-hand side of this image, you can see a couple of the moons of Saturn that he was able to pick out. But this is actually a sketch that's been reproduced since then, showing what Saturn looks like. So that was in 1852. In the 19th century, we went a little further still. We started not just have to rely on sketches and drawings, we were actually able to use photographic plates. So this is a photograph from 1888 of the Dumbbell Nebula, it's called. You can see this nebulous type structure of gas. It's a leftover remnant of a star. And these images are actually from the University of Cambridge. As you can see, historically, we've used photographic plates or simply our own eyes as the instrument that we might draw in these kind of circumstances. But if we come more up to date, things have advanced significantly in terms of the technology we have available. This is a fantastic picture that one of my colleagues, Ryan Ketra, let me use in the talk this evening. This is simply taken with a professional digital camera that you can go and buy from any electronics store today. This is a picture taken down in Arizona of the Milky Way. So in this case, a digital camera effectively is the instrument that will be used for studying the night sky. Not only can we study the Milky Way, as you can see this band in the middle of the image here, but we can also do some fantastic star trail images like this one you can see. It's great. This is looking towards the North Celestial Pole and Polaris and seeing the stars swirl around as the Earth spins on its axis. See, this is effectively an astronomical instrument studying the night sky, just a commercial digital camera you can buy. Now, as astronomers, we can go much further than simply going down to our nearest electronics store and buying a digital camera. We are trying to study things in more and more detail with our astronomical instruments. Things such as this. This is an image from the Hubble Space Telescope, that 2.4 meter telescope launched in 1990. It's 30 years old this year. And this is a picture called the Pillars of Creation. Now, the instrument, the astronomical instrument that was used to take this picture is the Wide Field Camera 3. It's designed to study and stare at patches of the sky for an extended period of time. And this Pillars of Creation is a big cloud of dust and gas where we have a huge number of new stars forming deep within these clouds. Wide Field Camera 3 doesn't just have to study these pillars of gas, though. It's also been used to study some of the most distant objects that we can see in the universe. This image here is called the Hubble Extreme Deep Field. It shows galaxies that are almost as far away as light has had time to travel to us from the beginnings of the universe. 13.2 billion years ago is how far away these galaxies are in terms of light years. So we can study close things by in detail. We can study incredibly, incredibly faint objects. To see these galaxies, we had to stare at this patch of sky for almost 23 days. And we did that not in one shot, but over many, many years, both using that Wide Field Camera 3 on Hubble but also the advanced camera for surveys. And we combine that data together to allow us to study these incredibly faint objects in the furthest reaches of our universe. To give you a sense of scale of the size of this image on the sky, this is a picture of the moon to scale, as you could go out and see when it's up in the sky and you have some clear weather. You can see that little box called the XDF. That same patch of sky is what you're looking at on the left, and you can see how small it is in comparison to the scale of the moon. So it's a tiny patch of sky comprising thousands of galaxies, and therefore we know that there are millions and billions of galaxies that now make up our universe from these types of observations. So these are the type of things we want to do as astronomers, to study these incredibly challenging things. But just how do we do that? And how do we design and build those instruments to study the night sky? Well, a bit of a spoiler for what's to come. There's lots of parts involved in that process. There's a design part. We then have to fabricate things, put it all together, test it, send it to the telescope, and then we start doing the science. We have to be really careful making sure we look after our data and keep it for future astronomers to look back, because that's becoming incredibly important that we keep a record of exactly what we looked at when we try to study how phenomena change over longer and longer timescales. But one of the special things about astronomy compared to the other sciences is we are limited by the light that comes from those physical phenomena we're trying to study in the universe. We can only measure that light. We can't do an experiment, particularly in a laboratory, to try and simulate the conditions that those phenomena exist in. We can do a little bit of it, but really we rely on the light coming from those phenomena. So we have to think a little bit about that light or that radiation and what we see from the different phenomena in the universe. Now, many of you have perhaps heard of electromagnetic radiation or the electromagnetic spectrum. This describes all the different colors of light, effectively, that we can see through the universe. Visible light, as you can see here in this image, is that small section of the different colors of light that our eyes are able to see. And if we describe light as a wave, just like waves upon the ocean, it's made up of crests and peaks and troughs. So the crests of the wave, the distance between them is what we call wavelength. And if we increase the distance between those crests, we increase the wavelength. We make it to a longer wavelength. If we bring them closer together, we go to a shorter wavelength. Visible light has peaks about 500 nanometers apart, or about 1/100th the width of a human hair. So it's very, very, very short distances for visible light. But we can stretch those wavelengths out, increase that distance between the crests to longer wavelengths. And that's where we get to things like infrared light, radar, radio waves eventually, where we go from nanometers out to meter wavelengths. We can go the other way to shorten them to ultraviolet, to X-rays, and eventually to gamma rays. Now, if we think a little bit about the radio waves for a moment, those longest wavelengths of light, we're talking here from something like tens of centimeters to meters or longer. There are many phenomena out here that emit radiation light at these wavelengths. One of the most important is hydrogen atoms. Now, hydrogen is one of the most common elements across the entire universe. 73% of the matter that you and I are made up of, which was created in the Big Bang, was hydrogen. So initially, we didn't have hydrogen atoms because the universe was too hot, because the electrons couldn't stay attached, as you can see in here in that blue electron there, couldn't stay attached to that red proton at the center of the hydrogen atom. It was just too hot and the electrons got stripped away. But today, as the universe has cooled, we have a lot of hydrogen atoms around in the universe. And they're good tracers of where all of the material, a lot of the matter is that you and I are made up of, that makes up the planets and the stars. So if we want to try and trace where the material is, we want to try and see this hydrogen. Now, quantum mechanics has a specific property on electrons and protons, and it's called spin. And if you think of it as basically an arrow, each of these electron and the positron, you can see there, that red positron and the blue electron, can either have an arrow pointing upwards or pointing downwards. Now, they would prefer to be pointing in opposite directions, but they can be pointed together. And what happens is very occasionally, these arrows going from being aligned to being opposite directions. And when they do that, they emit a radio wave. Now, for each individual atom, that process might only happen once every several million years. So it won't even happen in our lifetimes. But there's so much hydrogen gas around that we actually see this process happening all of the time. And it allows us to study, for example, the structure of galaxies. We can see the spiral arms in our own Milky Way galaxy, looking at this 21 centimeter radio emission as these sort of arrow vectors, these spin properties of the proton and the electron go from being aligned to being anti-aligned. So we can study where the matter is in the universe using radio waves. Another effect we can see is pulsars. Now, pulsars are leftover remnants of stars that come to the end of their lives. These are neutron stars. And as they come to the end of their life, they spin up and they emit radio waves, just like a lighthouse on the shore. If that's aligned to the planet Earth, we see these flashing radio waves coming towards us. And there's a nice little story about when these were first discovered. It was such a regular signal that Jocelyn Bell Burnell at the University of Cambridge thought that this could be extraterrestrials or something else. They discovered the first pulsar and it got the sort of naming on it was LGM1 for Little Green Men 1. Now, obviously, today we know a lot more about those and we've discovered a lot more things, but pulsars are incredibly important. They flash at a very, very, very regular interval. It could be many, many times a second, but we can use this regular timing to study the properties of the universe, understanding what's going on around the pulsar. And it's also a way we're hoping in the future to be able to study and look for gravitational waves. So these two phenomena we have to look at in the radio to be able to study them. Coming to shorter wavelengths, microwaves, something at the wavelength of like centimeters to millimeters. One of the key things that we study in this wavelength is the remnant of the cosmic microwave background. So I'm not going to delve in this into too much detail, but basically if we want to study the beginnings of the universe and the Big Bang, we need to study the night sky or even the daytime sky in microwaves, and we have to do this from space. Another thing we can look at is studying the structure of galaxies as well. We can look at, for example, molecules like carbon monoxide. It emits light at 2.6 millimeters in that microwave band, and we can use that for mapping the structure of the galaxies, just like we did with hydrogen. Coming shorter still, closer to the visible light that we can see, we can use infrared light. And this is wavelengths of sort of microns, about a few nanometers. It can be a few nanometers, a millionth of a meter. Well, if we look up at the night sky, just like that picture I showed right at the beginning of the Milky Way on that image, this is a similar sort of image, but taken of the whole sky, and we can see this band of dust and gas here across the middle. Now, when astronomers say dust, we tend to mean molecules that block the light coming from behind it. So there are billions of stars in our own galaxy, and you can see them in this band running across this middle of this image here. But you can see these dark regions blocking out that light, and that is the dust I'm talking about. Visible light, like our eyes can see in this image, can't pass through that dust. But if we switch to looking at infrared wavelengths, the light can actually pass through. So we can study the center of our galaxy in much more detail using infrared light compared to the visible light that our eyes can see. So that is one of the key reasons we can use infrared light for studying the universe. Also, if we want to study distant objects in the universe is currently expanding. So starlight from galaxies a long way away now actually appears to us in the infrared rather than the visible that the stars initially emitted it at. So we have to use infrared light to study the most distant galaxies in the universe as well. Coming to shorter wavelengths again, ultraviolet. This is an image of the Andromeda galaxy, M31. It's the nearest galaxy to our own Milky Way. And you can see that dust again here in the image. This is a visible image that you're looking at. If we switch to the ultraviolet, certain areas of this image pop out compared to the visible one. And this ultraviolet light is emitted by young, newly formed stars that are very hot. And so if we want to study how stars form, those stellar nurseries, we need to look at the night sky in ultraviolet. Going to higher energy still, gamma rays and X-rays. Many of you are probably familiar with X-rays, hopefully not too familiar with them from a medical perspective. In medical X-rays, what we're doing is we're passing the same X-rays we see coming from space, say exactly the same wavelength. We're seeing where they pass through your soft tissue and get blocked by your bones. So you see a shadow where the bones are, and you see a bright region where things pass straight through. Now, we don't block X-rays when we're studying them for astronomy. We actually want to collect them. So we collect those X-rays using space telescopes. And these are used to study some of the most powerful and high energetic systems in the universe, particularly black holes. And for those of you who came to the talk that Dan Wilkins gave about black holes a couple of months ago here at Notre Dame, you learned a lot about them then, but they're some of the most energetic phenomena in the universe. This is a picture, an optical picture actually, of a cluster of galaxies called the Perseus cluster. Right in the center of this, there is a supermassive black hole. And what it's doing is heating gas up to millions of degrees Celsius. That's what you can see here. And then there are these dark regions right in the center. And this black hole is emitting jets, blowing bubbles effectively in that gas. So if we want to study these black holes, these highly energetic phenomena in the universe, we really have to study the X-rays and the gamma rays coming from the universe. So that's why we have to have a whole suite of instruments to study this entire electromagnetic spectrum. With all those phenomena, we want to try and build up a whole picture of how the universe works. We can't just study one part. We have to study it as a whole to piece together how the universe works together from the Big Bang to where we are now. We can't just look at one thing, we've got to look at them all. And that means we have to design very different astronomical instruments to look at these different phenomena. Well, let's think about how we might go from the science, the phenomena we're trying to study, to an instrument design. What exactly are we trying to measure? Well, if we're looking at black holes, we want to look at X-rays. If we want to look at hydrogen, we want to look at radio. So what wavelength of light do we need to look at for the phenomena we're trying to study? How bright are the objects we're looking at? Some objects are incredibly bright. They might be quite close to us. Some, like that image from Hubble, that Hubble extremely deep field, they might be very, very faint. How bright are the objects we're trying to study? How big does the object on the sky appear? It's not necessarily how physically big it is, because a small object close by could appear to be the same size on the sky as a very large object a long way away. So how big does it appear on the sky when we look at it? And then sometimes we worry about how fast does the object change. If we have to stare at it for 5 minutes to be able to make a measurement, but it changes every 10 seconds, we're not necessarily going to get the best understanding of how the universe works there. So we take these sort of 4 big questions and trying to use those to drive the instrument design to make sense of what we need to do to study the physical processes we're trying to see. Now, we tend to want to try and make these measurements on the ground. It's a lot easier if you can go to a telescope, install an instrument, maintain it, check it works, adjust it. But sometimes the Earth's atmosphere just says no. Now, as astronomers, sometimes we joke that it would be a lot easier not having the atmosphere here on Earth for our science. We could do everything on the ground there. But as humanity, we definitely want to keep that atmosphere around for our own survival. What you can see here is a graphic that shows basically where the Earth's atmosphere blocks the light. So on the left-hand side here, you can see atmospheric opacity. If it's at 100%, it means no light gets through. If it's at 0%, it means all the light gets through the Earth's atmosphere as it comes from the stars to us on the ground. So those gamma rays and X-rays and ultraviolet all get blocked by the atmosphere. We can't measure those on the ground. We have to do it from space because the atmosphere gets in the way. The infrared is problematic. Some of that gets completely blocked. Other parts of it get partly blocked due to water vapor in the atmosphere. Sometimes we're able to get around that by going to very dry places on Earth, like the Atacama Desert in Chile. But other times we really have to go to space to make some of these precise observations. At very, very long wavelengths, something like tens of meters, we don't get any radio waves passing through the atmosphere either. This is due to the Earth having what's called the ionosphere, and basically ultraviolet light from the sun collides with atoms in our upper atmosphere on Earth, and it basically prevents these wavelengths of light getting through to the ground. So if we've decided we're going to be on the ground, the question next is, how faint an object is it, and how big a telescope do we need? Now, we're not very original with our naming in astronomy. So you might only need a very small telescope, something like this, the Killer Degree Extremely Little Telescope. You might need something like this, which is the Very Large Telescope. So this is a telescope on the left that's about 4 centimeters across. The one on the right is 8 meters across. We are currently building the extremely large telescopes. They're about 30 meters across, but we can't yet figure out how to or afford to build the next generation beyond that, which is called the OWL, which is the overwhelmingly large telescope, although we did think about it. So we're not very original with our naming, but we have to think with these things, how we actually decide which size telescope we need for the science we want to do. Well, one of the questions is about how bright the object is. And that comes back to that light bucket we talked about right at the beginning. If an object is very faint, we need a big telescope. If it's very bright, we can maybe use a small telescope. But there's a second phenomena called resolution that comes into this process when we're talking about telescopes. Now, resolution is effectively the smallest detail you can see when you're staring at the sky. And it's governed both by the wavelength of the light that we're studying and the diameter of the telescope. So we want to make resolution as small a number as possible in this equation. So we can't change the wavelength, that's set by the phenomena. So we can make telescopes bigger to get a better resolution so we can see more detail on the objects we're studying. So back to you guys. I'm going to ask you a question now. How big is the world's largest telescope? There are 4 answers here, 1.2 meter, 10.4 meter, 500 meters, and 12,000 kilometers. If you go to the web address, you can see that at the top of your screen on your devices, you can fill in those answers and we will see what you guys think is the answer to this one. Okay, while the rest of you are still filling that in, let's see what you think the answer to is on this one. So we've got a lot of people saying 12,000 kilometers. Then we've got a mix for 10.4 meters and 500 meters as well. We have some people talking about the smallest telescopes as well. Just give it a few more seconds and then we'll see where we're at with these responses. Okay, well, there seems to be people are leaning towards 12,000 kilometers here is their answer. And I will say to you that whatever you selected here is the correct answer, because I didn't really define what the world's largest telescope really meant. So whatever you said, you're going to get the right answer on this one. If we're talking about X-rays, the Chandra X-ray telescope has a physical diameter on its mirror of about 1.2 meters. The largest visible telescope in the world, you can see here in the bottom left, is the Grand Telescopio Canarias, and that's below that image of Chandra that you can see, that X-ray telescope. At the top right is the largest single aperture telescope in the world. It's called FAST, and it's the 500-meter aperture spherical telescope. So it's 500 meters across from one side of that telescope dish to the other. And then that 12,000 kilometer answer is from the Event Horizon Telescope, where we can connect multiple telescopes together to take an image which has an effective size of a telescope 12,000 kilometers across when we're talking about resolution. So no matter what you said there, you were right at some level. Typically, we would talk about an optical telescope being the biggest telescope tends to be the criteria, and that would be the Grand Telescopio Canarias, or for the single largest aperture telescope in the world, that would be the FAST telescope you can see there on the top right. But whatever you said, you were right on this occasion. One of the world's largest optical telescopes is the one I actually primarily work on. And this is the Large Binocular Telescope. Again, we're not very original with our naming, but the LBT, as it's nicknamed, the Large Binocular Telescope, has two 8.4 meter mirrors. You can see them here in the image. And I use this for building eye locator, the spectrograph I work on, because we are looking at stars to see signatures of planets, but we spread the light out coming from those stars into many different colors, just like passing the light through a prism or a raindrop. Now, we take simultaneously somewhere between 150,000 and 200,000 images effectively. So we need a lot of light to be able to do that. And that's why we need that big telescope. Just to give you a sense of scale, if you look at this image, right down, we'll go back one. If you look at this image, right down at the bottom here, that's one of the staff at the telescope working on the telescope when I was visiting previously. So that gives you a sheer sense of scale for the LBT. This is a telescope down in Arizona at the Mount Graham International Observatory. Now, coming back to the Event Horizon Telescope, this made news last year, and primarily because it was able to take the first ever image of a black hole. So if we come back to light and think of it as a wave, if we take two waves on the ocean and we align the crests together, those waves will come together and give us a bigger peak, a bigger crest of a wave. If we take a crest of one wave and a trough of another and bring them together, they'll sort of flatten and cancel out. And if we record the light at an array of telescopes at exactly the same time, we can then measure when the crests and the troughs arrived, combine them together, and we can make an effective image of a telescope in resolution size that is the distance between those two telescopes. So for the Event Horizon Telescope, one of the largest baselines, as they call them, was from the South Pole to Greenland, and they're going to start using those again in the future. But you can see they have all of these different distances between them to get them effectively very, very large baseline telescopes. Now, of course, as I mentioned, you can't always get these observations from the ground. And sometimes you have to go to space. And that's what we did with the Hubble Space Telescope. And we are currently building its successor, the James Webb Space Telescope. It is a 6.5 meter mirror. You can see here when it was being assembled at the NASA Goddard Space Flight Center a few years ago now. See those mirrors deployed, and it's going to be studying the distant universe and those distant galaxies. So we've got our telescopes, but we also need to record our images. And we do that using CCDs. Now, many of you may be very familiar with these. They're effectively just like you might have in your cell phone or in a digital camera. The CCDs we use for astronomy, while they're fundamentally the same thing, They tend to cost a lot more, and they've been very precisely manufactured to have very, very, very good characteristics for looking at very faint objects. Usually we have a lot of very precise requirements typically on these cameras. The image you're seeing here is the array of CCDs that was built for the Kepler satellite that was launched in 2009. Now, you might be used to thinking of digital cameras as a few megapixels. This focal plane array, as we call it, is an array of CCDs. There's 21 CCD chunks there, and they're basically aligned in pairs, has a total of 95 million pixels, or 95 megapixels. That was back in 2009. Today, we're building a ground-based equivalent of this for the Legacy Survey of Space and Time, LSST, which is going to take place at the Vera Rubin Observatory in the coming years. That comprises 189 individual detectors. Each one is 16 megapixels, and that gives you a total of 3.2 billion pixels per image that instrument is going to take on the back of that telescope. So that gives you a sense of what we're doing with these things. But just like your digital camera, your cell phone camera, if you've tried to use that when things are very faint, you may not get good characteristics. Your images might look a little bit noisy. This is sort of a schematic that shows some of those noise characteristics that you might see on some of your images you take. You can see on the left here, everything looks a little bit grainy. And as we go to the right-hand side, things look a lot cleaner and sharper. Now, this is using ISO speeds on cameras and things like that if you're familiar with photography. But in astronomy, we work very, very carefully to try and get to that right-hand side of the image. We have nice, clean images. We've often cooled our cameras down very significantly to remove a lot of electronic noise that comes in. We also do very careful calibration of the detectors to try and make sure we can remove these characteristics as we move forward. So that's one of the things we have to be careful about for the detectors at the end. So we've got a telescope, our detectors, and then we have to fit into that middle piece. And we do that pretty much through optical design. We say we've got a telescope, we have a detector at the back. How do we take the light from the telescope and put it onto that detector? Well, it might not seem very technologically advanced, but typically we start with a simple pen and paper. We know what we're trying to do, and we'll sketch up some kind of conceptual design to figure out roughly what we want to do. So we might need to magnify the image or demagnify the image to fit it onto a detector. So we make rough estimates of what we're trying to do. We then move on pretty quickly, and we start going into software simulation to account for real effects. Now, you might have played with a magnifying glass trying to focus light from the sun down from that to set something on fire. Please be careful if you do that. And you might think, oh, it's great, it focuses all that light. Well, actually, the different colors of light focus at a slightly different distance from that magnifying lens. And if we're building precision instruments, we have to account for this and many other types of effects. So we use a lot of different software simulation to do this. For eye locator and injecting light into fibers at the LBT, this is what our optical design looks like from that simulation. You can see the beam from the telescope coming in here. It comes in from the telescope. We reflect it through a load of mirrors, pass it through some lenses, through other mirrors, and separate, sort of dividing the light out by different colors. And then we put it into a fiber here, and we put it into a camera here. So we have this all in a computer simulation. One of the specific components we have here is this two set of prisms, as you can see here in the image. And if I just zoom in on that, these are actually to correct for an effect of the Earth's atmosphere. It acts like a prism, separating the lights out into its different colors, and we actually want to bring it back together. So we have a set of prisms that basically counteract the effects of the Earth's atmosphere. So we take this optical design, we do a lot of analyzing and make sure it's going to work. And then what we do is we actually go out and get those components fabricated. So if I just flip back, you can see that right-hand prism there. You can see the three pieces of glass that are all put together. And then you can see this here assembled in the lab, delivered by one of our vendors as we were building this instrument together. So we get all those optics fabricated based on the design. What we then say is, great, we have these optics, but we can't just, they don't just float in the right place on their own. We have to build some way to support them. And that's where we go through a process of mechanical design. So you can see here, if we look at this lens, the first lens here in the system, this actually sits in this little tube here. Those prisms I just talked about here, they actually sit in these two stages that rotate them around as the telescope moves. The mirror here, and that's in here, that camera I talked about down in the bottom, and a fiber that we put in the system here. So we basically take that optical design and then say, let's support the optics in a mechanical design. And this is just a rendering that we did from one of our software programs. Eventually, you build it from that CAD model. This is the process where we were assembling that fiber injection system. And eventually, you put it all together. We tipped this up in the laboratory at Notre Dame, added a whole load of electronics because we need to be able to move the components. And you can see those here in the door. And eventually, the whole system is assembled and you start testing it. This is one of the graduate students, Andrew Bechter, going through and doing all of that testing. Always looks cool in the lab where you've got your laser glasses on and you've got all the lights on. It's a very cool picture. But what I want to show you a little bit is how we do that testing process. So this is our Notre Dame lab equivalent of the Large Binocular Telescope. We actually simulate the beam characteristics coming from the telescope, and we pass it into our system to check that everything performs how we expect it to. We go through that process, make sure everything's right, fix anything that doesn't work, and then we're ready to send it down to the telescope to be installed. Of course, there's not just that specific part of the instrument, there's all the additional things that come with it, all of the power controllers, everything else. You can see Andrew and my other colleague, Brian Sands here, we were installing 40 meters of fiber to connect that injection system, the fiber injection system you just saw being tested, that'll connect to the instrument spectrograph and another part of the telescope. So this was in the hallways at Notre Dame a couple of years ago now. We were busy putting through all of the fibers into conduit that eventually got, you can see it laid out here in the hallway, that eventually got installed at the telescope by some of the telescope staff. So it's not just the instrument itself, it's all the additional components that come with it. So when it's all ready, you basically then take it all apart because you have to ship it from Notre Dame, in this case, down to the Large Binocular Telescope in Arizona. And we do this primarily using large metal shipping boxes for our case. Each instrument's a bit different depending on its size and weight and requirements. But this was me in the lab a few years ago, packing away our prototype instrument after doing a lot of lab testing, taking it apart, ready for shipping. We then load everything in the back of a truck. You can see it all wrapped up here for shipping down to Arizona. And then eventually it gets all the way down there and we drive it up a mountain road. This goes up to 10,000 feet and part of the road isn't paved. It's a non-paved surface. So there's a couple of images you can see here going up in the winter. The view off to the left-hand side and also straight ahead, as you can see in these. It can be a very rough ride. So you need to be very careful with fragile instruments not to damage them in the process. As a slight side note, not only did the instruments go up the mountain, when the telescope was built, everything also went up that access road. So this is one of those 8.4 meter mirrors being transported up the side of that mountain on the back of a low-loading truck. So you really get a sense of some of the challenges that we have to go through to do our science. Now, when you get to the telescope, you basically have to put everything back together that you shipped. It took apart at Notre Dame, you have to put it back together and you retest it to make sure the performance is still the same as you got in the laboratory at Notre Dame. Eventually, after that testing, you go and install it. This was the final system we installed last year at the telescope. You can see it in that blue box. But we'd also previously installed a prototype system at the telescope. And you can see that here. This is me installing it back in 2016. And it was a bit of a nerve-wracking day. This was one of these 8.4 meter mirrors right behind my heels there. So we were very carefully strapped in, making sure we didn't drop any tools. They were all secured to the harness you can see me wearing there. So once the instrument's installed, we check it out again, we go on Sky, and fingers crossed everything works. You can see Andrew Bechter, Eric Bechter there, Justin Krepp, who's the PI of the instrument, and me in the background. We have a lot of monitors monitoring all those electronics, all of the equipment, all of the cameras. We have a lot of servers managing all the data, recording it. And if it all works, you get a very happy instrument team at the end of it. And this was the first time we put it on the telescope, and it worked remarkably well. So we were all very, very happy. So it's great when everything works the way you expect it to be, and you can go out and buy all of the hardware you need. But of course, that might not be the whole story. So it's time to ask you another question. What do you think some of the challenges might be for building these type of instruments? So if you go back onto that website again, you'll be able to fill in some words and things, and we'll give you a couple of minutes to fill those in, and then we'll see what your answers are. So there's some great answers coming in here. So let's talk through a few of these. There's lots of you talking about money. And yes, money is always a challenge in these things. Instruments themselves, actually, the hardware in them often is not the driving factor in the cost of these instruments. It's because you need people that really have very precise sets of expertise, and they are highly qualified people, and so you have to pay their salaries. And that tends to be actually the driving cost in building these types of instruments. The other thing that's often challenging is we are doing a lot of custom fabrication. You obviously try to go out to work and buy pieces of hardware if you can that exist out. You can just go and buy off the shelf, as we call it, go to the vendor and just immediately get it the next day. But often we're doing very, very, very precise things that need custom designs. And if it's lenses and things, there's lots of companies that can do that to very, very high quality. So that's great. You also have to check in shipping. You don't break it. Things can be fragile. Certain types of glass, for example, if they get water on them, they actually basically become opaque. So they're almost like a salt. So you have to be very careful with how you treat those, keep them in low humidity environments. You also have to, as I say, with shipping, you want to make sure you don't break something. One of the answers we had there was you forget and leave your tools at home. If at the top of a mountain in Arizona, you can kind of get 2-day shipping, but you really don't want to forget anything that you can. And we end up taking almost effectively the entire lab down from Notre Dame to Arizona when we go. And there are facilities at the telescope, but you always want to make sure you have access to everything you want. Now, we have to calibrate very carefully. You have to make sure things work. Of course, there is always the point of no vendor is able to provide the instrument and hardware you need, and you have to improve the technology. For example, a lot of the drive at the moment in astronomy is improving those detectors that record our images so we don't have as much noise, or they're more efficient at turning that light to an electrical signal that we can record. We might want them to be more efficient, and we might want them to have less noise on them so we can see fainter and fainter objects. Another thing on telescopes on the ground is perhaps atmospheric effects. Turbulence can distort the incoming images, so we might need to correct that. And we can do that with things like adaptive optics, where we measure the distortions of the atmosphere and correct them thousands of times a second. That's needed for actually eye locator at the LBT. We can also try and use chance. If you take lots of images in very quick succession, some of them will be very distorted by the atmosphere, some won't, and you can just use the good images for doing your science. So we can get quite clever with some of the techniques. It may be a case, though, that the technology doesn't physically exist. And a lot of the time then you start developing new technology. One of these I want to highlight that we tested down in Arizona last year was 3D printing of an array of lenses on the tip of an optical fiber. Now, to give you a sense of size here, this pencil I'm holding up, the tip of that is about the size of this area you can see here on this fiber tip. And we are 3D printing a set of 6 lenses around this to allow us to see if the beam moves off our fiber at the telescope in Arizona, to allow us to get more light into those fibers and improve our science. So we start developing new technology where we need to, where no commercial product exists. So after we do all of this, we build a great instrument, we test it in the lab, we put it on a telescope on sky. Well, what happens if you don't discover anything? You know, you went to the science and you go out and make those measurements as best you can and you don't see what you expected. Well, if your instrument's well built and you understand it, and you don't see a signature that you should be able to detect, what that might tell you is our theory and our understanding is wrong. So when we come up with the science we're trying to study, we have a theory about how the universe works. So we know what we should be able to detect if that's right. But sometimes it's not right. And so we end up having to go back and assess that our theory is completely wrong. We didn't get the signature we were trying to detect. And that can be as powerful a result as actually detecting something. When we kind of break our theories, that's usually when we get an extra insight into how the universe might actually work. So in summary, today we are building a huge number of different instruments for telescopes, both on the ground and up in space. And these instruments can be on some of the biggest telescopes, like you can see here. This is the 8-meter Very Large Telescope in Chile, or it can be something no bigger than a digital camera. It can either be for a spacecraft far from Earth, or it could be a spacecraft just in orbit above our heads right now. But all of the instruments that are designed for all of these telescopes study the phenomena across the entire universe, collecting light of different wavelengths, from radio waves through to short wavelength gamma rays. And we use a combination of all of these different instruments and telescopes to study how the universe works together as a whole, and furthering our knowledge of how that cosmos pieces together, coming from the Big Bang to where we are today. So I want to leave you with a mention of one final astronomical instrument, which is aboard one of the most distant man-made objects from the planet Earth. Back in 1977, the Voyager 1 and the Voyager 2 spacecraft were launched from Earth, and they were designed to study the outer planets in our solar system. Now, for decades, the data from these spacecraft has provided us some of the best information we have of Jupiter, Saturn, Uranus, and Neptune. And these spacecraft are still actually going strong today. On the 14th of February in 1990, 13 years after Voyager 1 had been launched, it was on its journey out of the solar system, and it was 3.7 billion miles away from Earth. Today, it's almost 14 billion, so it's kept on its journey, moving further away from the center of our solar system. Now, in February 1990, the famous astronomer Carl Sagan requested that NASA commanded Voyager 1 to turn around and look back in the opposite direction to where it had come from and take a portrait of the planets it had visited, starting with Earth and moving further out. So they commanded the spacecraft to turn, and this is what they saw. Now, being so far away from Earth and the sun at the outer parts of the solar system, to get that image of Earth, you have to look pretty close to the sun. And what you're seeing here are bands of light that are effectively lens flare coming from the instrument camera on Voyager 1. Now, if you look very carefully between those two white lines you can see on there, there's a very tiny dot. And if I just zoom in, that tiny dot is the planet Earth. This is the most distant image ever taken of Earth. Upon seeing it, Carl Sagan said the following: "We succeeded in taking that picture. And if you look at it, you see a dot. That's here, that's home, that's us. On it, everyone you ever heard of, every human being who ever lived out their lives, the aggregate of all our joys and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals. Every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. So I'm going to leave that there for today. I hope that's given you an overview of how we are able to study the universe and the instruments that we need to do it. If you have any questions, obviously, please put those into the chat on YouTube or the chat on Zoom or through the Google form. And we'll poll those together, give you a couple of minutes, and then I'll answer any questions you have. So thank you all very much. So a couple of questions that have come in so far. Do all elements emit electromagnetic radiation because of opposing spins? It very much depends. They all do, but they're not necessarily. It very much depends upon the element itself. It's to do with the atomic structure. We also have ways that the electrons can move around in the atoms and emit light as well. So that tends to be more visible light we see. It just really depends on the quantum mechanics process and the exact atom to what's going on there. But a very good question. Another question that was related to perhaps the challenges and things, how long does it take to build an instrument, and do they always work the first time? That was a question from Michael. That is a great, great question. So I've been working on iLocator now for 5 years. We're still building that instrument at the moment. It should be at the telescope in the next year or two. And so it's a constant process. It really depends on the complexity of the instrument, if it's perhaps an incremental upgrade, or if it's sort of something completely new, which iLocator is. And as to whether instruments work the first time, I will point you to the example of the Hubble Space Telescope. When it was launched, the image quality was not what it should have been. And so effectively every instrument that's now in Hubble is fitted effectively with a pair of glasses. The optics in the original Hubble Space Telescope was very, very, very slightly misformed on the primary mirror. And so they actually correct that effect in the other optics in the subsequent instruments we put on there. So great question. If it's on the ground, it's often easier to fix, and we go through a lot of laboratory testing. NASA does much more testing now of all of their spacecraft than they did when Hubble was being built, because of a lot of lessons learned from that process. Great question. Another question from Rebecca. How do you decide whether it's better to put the telescope in space or on Earth? If you can put it on the ground, you tend to, because it's much, much cheaper than putting it up into space. Launch costs for spacecraft are incredibly high, and because you can't go up and fix them, you have to do a lot more testing and engineering than you do on the ground. If it breaks on a telescope in Arizona, I can go down there and I can fix it. So it's cheaper typically to build instruments for ground-based observatories than it is in space. But very good question there. Another question that's come in: what is the most unique astronomical object you've seen using the instruments, and how did you decide what it was? Well, when we were commissioning and doing the sort of first observations with iLocator back last year, because of the size of the telescope and the wavelength we're looking at, we have a really, really high resolution. We can see things in lots of detail. And a lot of the stars we went to look at initially, we wanted to just see a single star. About 3 of them were actually binary stars, 2 stars together in orbit around each other. And so it's the moment of where you kind of go, it's another binary star. But no one else has ever seen that before. And I think there's a real excitement about that for scientists. We're actually doing more analysis on that object presently. So it's a really exciting time for the instrument, and I'm sure we're going to discover a lot more things as well. I'll take a couple more questions. There was one, what's an essential feature to have in a telescope control system? So all of the components in a telescope and an instrument, you have a lot of mechanisms that might move lenses, they might move mirrors, all kinds of things. I think the most important thing at some level, from a user perspective, is can you actually move them all? However, from a telescope perspective, the thing that perhaps you might want to know about the most is something going wrong in your instrument? Because you might be operating this instrument remotely, you're not on the telescope yourself. And so typically you have a lot of alarm features that have been programmed that if something let's say gets too warm or you can't communicate with it, immediately tells an engineer or a scientist that something's up so they can take a look at it. Because I think we don't want to damage our instruments. We really want to make sure that everything's well tested in those criteria that something might be going wrong so we don't do permanent damage to the instrument. There is one final question that I'm going to take up here, which was a nice one to finish on from Sarah. And it was, what's the most exciting instrument coming up? Personally, I think one of the most exciting instruments is probably going to be the LSST survey that I talked about on that Vera Rubin Observatory. It's designed to study the transient universe, so how things are changing over time. And it's going to study the night sky in a huge amount of detail, with issuing thousands of alerts per night of things that have changed, so we can go and look at them with other telescopes in more detail. So I think it's really going to revolutionize astronomy. It's going to give us a whole new way to view how the universe is changing, because I think we tend to think of it as quite static, but it really does change quite rapidly if you're able to measure it precisely enough. And I think that's really going to change our knowledge and understanding, although there's a huge amount of data that comes out of that thing with those billions of pixels. So it's a big technological challenge of making all of that work together, but I'm sure the engineering people will be able to do that in the future. I just want to finish and wrap up by highlighting our talk next Tuesday. And we're going to invite Dan Wilkins back from Stanford University, and he's going to be talking about Born from the Stars. That's at 7 o'clock Eastern time again next Tuesday. And I hope we will all see you then. As a reminder, please go to our website, nduniverse.org, if you want connection information or to sign up for our mailing list. And you can also find us on Facebook. Thank you all very much for joining us this evening, and hopefully we'll see you next week. Stay safe. Thank you.